Hi, maybe you have already heard about the concept of a carbon budget, but if not, it's actually quite a useful concept to learn more about and to understand why we have to have quite stringent climate policy in order to meet the goals of the Paris Agreement. But maybe I should introduce myself first. My name is Detlef van Vuren, and I'm a senior researcher at the Netherlands Environmental Assessment Agency, and I'm also a professor at Utrecht University, and I was a lead author on one of the latest set of IPCC reports. So, in explaining the carbon budget, let's start from the basics. As the Earth is being warmed by the sun, and if that was the only story, then it would be about 30 degrees colder than it is today. And this planet is livable thanks to the natural greenhouse gas effect. And all kinds of gases in the atmosphere that trap some of the outgoing radiation of the Earth and send it back and make the world a livable place. Yeah, by now we have all kinds of humans who are living on this planet as well. And by burning fossil fuels, by agriculture, and by deforestation, they put more greenhouse gases into the atmosphere. Yeah, and it's not so difficult to understand that that would lead to more warming and therefore the enhanced greenhouse gas effect. Now, of those gases, I would like to concentrate for a moment on CO2. And CO2 is by far the most important contributor to the enhanced greenhouse gas effect, but it's also, for practical purposes, very, very long lived. Yes, some of the CO2 goes in from the atmosphere into the ocean, and some of the CO2 goes from the atmosphere into the biosphere. But yeah, a considerable part also stays for a very, very long time in the atmosphere, and you can see that it slowly decays over time. Yeah, interestingly, the warming itself is somewhat delayed, and these two effects together actually means that there is a linear relationship between the amount of CO2 that is in the atmosphere and the temperature increase. Yeah, and that you can compare to a bathtub. Yeah, we put the amount of CO2 in the atmosphere, and that leads to warming, not the annual emission, but the cumulative emissions. Just as in the case of a bathtub, if you open the tap, the water accumulates into the bathtub, and it's the level of the water that is comparable to the amount of CO2 in the atmosphere, and that determines the amount of warming. So cumulative emissions determine the amount of warming. Yeah, we can also see this in the climate calculations, in the models that we have of climate change. What you see on the graph here are the latest set of scenarios that were used in the last report of IPCC. And they, they show the emissions over this coming century, and they start at 40 gigatons of CO2, which are more or less the current emissions. And then, yes, emissions could go up and follow the red line on the top, or they could go down and follow the blue line on the bottom, but we all kinds of trajectories of future CO2 emissions. Yeah, we can use all kinds of climate models then to calculate what the temperature impact would be of such amount of CO2 emissions. And I've shown that here on the graph on the right by plotting the amount of cumulative CO2 emissions, so the amount of CO2 that goes into the atmosphere versus the calculated temperature increase, global mean temperature increase. Yeah, part of this graph is actually the historical period. That is that wobbly part that goes into the middle. And that is showing that we are, as humans, since pre-industrial period, already have emitted around more than 2,000 gigatons of CO2, leading to about 1.5 degrees of warming. Yeah, and if we then plot the impacts of all the different scenarios on top of that, we see that the blue scenario and the highest scenario leading all to further warming as a result of these cumulative CO2 emissions. Yeah, and as we already saw from the bathtub model, we expect the cumulative CO2 emissions to be linear with the temperature increase, what we see here very well. I can summarize it also by this graph. And again, cumulative CO2 emissions on the horizontal axis, the temperature increase on the y-axis. And you see this relationship, but you also see that there is a band. And the bandwidth is caused by different models. We have models that suggest a stronger relationship between cumulative CO2 emissions and temperature. And we have models that show a less sensitive relationship that determines the bandwidth, but at the same time there is quite a strong agreement, and that uncertainty range is actually not that big. We understand the system relatively well. Yeah, temperature increase leads to all kinds of impacts that are detrimental. Sea level rise, they can lead to impacts on agriculture, impacts on human health, on biodiversity, all kinds of things that we really want to avoid. And therefore, as humanity, as nations, we already agreed that we want, in the Paris Agreement, that we want to keep global mean temperature well below 2 degrees. And if we want to pursue efforts as well to simply limit it to 1.5 degrees. So what would be needed for that? And we can now use that same graph that we have here to easily see that. And we just have to fill in something like well below 2 or 1.5 degrees. And then we can read out the graph and see how much CO2 emissions you're allowed to put into the atmosphere to stay below that particular level. And that's not a lot, recognizing that we have already emitted 2,000 gigatons of CO2 or more. Then you can see in this graph that the amount of CO2 that corresponds to the Paris Agreement is maybe a few hundred gigatons of CO2. Yeah, in reading off this graph, we actually have to make a decision. Which model do we believe? Do we believe the most sensible model, or the most sensitive model, or the less sensitive model? Yeah, it makes sense to read at least the median, so the 50% here indicated. And yeah, climate scientists would also argue only reaching a climate goal with a 50% chance might not be enough. And so you might want to have a larger chance, like 67% chance, to stay below a certain temperature goal. And so these are typically the values that we use then to calculate the amount of CO2 that we can emit, or the so-called carbon budget. And there was this publication earlier this year by Piers Forster et al. That calculated the carbon budgets again. And they use a slightly refined method compared to the graph that is showing here. They have simple climate models that they calibrate to the outcomes of bigger models. But then, in principle, it's the same type of calculation. And the results are shown on the left. And so for this 67% chance, a 50% chance, and for staying below 1.5 degrees, 1.7 degrees, and 2 degrees, they provide the carbon budgets. And the carbon budget for 50% chance to stay below 1.5 degrees is 130 gigatons of CO2. You can compare that to the 42 gigatons of CO2 that we emitted in 2025. So only 3 times the current emissions. Yeah, for 1.7 degrees, and then with a 67% chance, it's about 400 gigatons of CO2. For 2 degrees, 67% chance, it's about 900 gigatons of CO2. Yeah, so I already compared it to current emissions. This is done in this next graph as well. Here I simply express the carbon budget in terms of 2025 emissions. And so you can interpret it as how many years of the current emissions can you still allow before you exceed this carbon budget. Yeah, and for 1.5 degrees, with a 50% chance, that is 3 years. So that means way before 2030, we will exceed that carbon budget. If we then look at 50%, 1.7, it's about 12 times current emissions. And for 67%, 2 degrees, it's 20 times current emissions, meaning that by 2045, if we continue emissions at current level, we would exceed also the 67% chance of staying below 2 degrees. This is not a lot, and I can illustrate that on this graph. Here you see on the horizontal axis time, on the vertical axis the emissions, and you see in 2025 we are slightly above 40 gigatons of CO2. And what you see as well is in the orange line our best guess for the impact of current policies. So we make projections for population, take a best guess here for economic growth, but also for current climate policies. We continue in the future, and emissions more or less stabilize. What you see as well is the carbon budgets. The carbon budgets for 67% well below 67% 2 degrees and the 50% chance of 1.5 degrees. The latter in blue and the first in purple. And you can see that they follow completely different trajectories if you want to constrain the emissions to that. And so you have to go down almost vertically for the 1.5 degree carbon budget and reach net zero just after 2030. And for well below 2, or for 2 degrees with 67% chance, slightly after 2060, you would have to be at net zero. Yeah, completely different trajectories. So it shows you how stringent the carbon budgets are that are comparable to the Paris Agreement, and how fast we will start to have to reduce our emissions to stay within those goals and to avoid the climate impacts that we want to avoid. And this is not completely the whole story. There luckily is a little bit of a flexibility as well, but it's not a lot. And that's in the story so far, I've concentrated on the tap, on the amount of CO2 emissions that we can put into the atmosphere. But luckily, there we can also play a little bit with the sink. And there are ways to take CO2 out of the atmosphere. And one of them is afforestation. Trees, if you have new trees, they will take out CO2 from the atmosphere. We have also a technique that is called direct air capture, where we take CO2 directly from the atmosphere and store it on the ground. You could, in principle, do the same with bioenergy and take the CO2 from the fume gases and store it on the ground. And yeah, those techniques could make the sink a little bit faster. But they have limited potential. Yeah, first of all, there's limited storage available in reservoirs on the ground. There's also a limited area where we can do reforestation or grow bioenergy. And on top of that, reliance on sinks in order to come back into the carbon budget means that you also temporarily overshoot the climate target. And then for a period of time, we'll still have the temperature that you were trying to avoid. And so that automatically means that the amount of CO2 that we can take from the atmosphere or willing to take from the atmosphere is quite limited. Maybe a few hundred gigatons of CO2. Now we can, with models, then try to design pathways that are consistent with the carbon budget. And I'm showing that here in purple for scenarios that are giving you a 67% chance of staying below 2 degrees, and in blue scenarios that are consistent with the 1.5 degree target, using some negative emissions. And you can see then, in that case, it might be possible to go to net zero for 1.5 degrees around 2050 and around 2070 for 67% chance on 2 degrees. In both cases, still emissions need to go down very, very rapidly to stay within the carbon budget. And so I've used the carbon budget concept here, and the carbon budget concept is defined as the amount of CO2 that corresponds to a peak in global mean temperature, or the target that you would like to achieve. And for 1.5 degrees, as I showed, the budget is only 2 to 3 times the current emissions. For well below 2, it might be in the order of 10 to 20 times 25 emissions. but in both cases, it's simply a very small budget, and we will have to reduce emissions globally really rapidly to to comply to the Paris Agreement. Yeah, and so I think that therefore this carbon budget is a very useful concept to simply understand what we need to do to stay within the Paris Agreement. Thank you for your attention.